All right, we're continuing talking about geometric vectors, and we have recently came up with very natural rules for adding geometric vectors together and multiplying them by numbers. And that was great, but when you're studying mathematics, simply inventing new operations is not quite enough. You must also make sure that they satisfy some essential properties, and that's exactly what we're going to do in this video. We will make sure that the rules we came up with satisfy commutativity, associativity, and distributivity. And that's a very important step in studying mathematics in a disciplined way, and will also give us an opportunity to interact with geometric vectors, which is exactly the kind of practice we need. And these properties may look innocent enough, but you'll see in a moment that when we try to interpret them geometrically, things will get a little bit involved, and that's perfect. That's exactly what we're looking for. So let's start with commutativity, a plus b equals b plus a. Or in words, when you add two vectors, according to the rule we came up with, the order of the terms doesn't matter. But what does it mean geometrically? Well, let's take a look. A plus b can be interpreted as two successive journeys, one according to the vector a and the other according to the vector b. And that's what I have displayed here geometrically. We start at the origin, we travel according to the vector a and end up at this point, and then from this point we travel according to the vector b and end up at this point, which is captured by the vector a plus b. Now, what would happen if you traveled according to the vector b first from the origin, and then from wherever you end up, you took a second journey according to the vector a? Would you end up at the same point? If you do end up at the same point, then a plus b equals b plus a and commutativity holds. If you end up at a different point, then vector addition simply doesn't satisfy commutativity. It is not commutative. So let's see if we end up at the same point. So our first journey will be according to the vector b. I guess it would put us right here. All right, and then from this point, we'll take a second journey according to the vector a. Right here. And do we end up at the same point when we traveled according to the vector a first and then according to the vector b? Well, I think so. Maybe someone who's a stickler for mathematical rigor would say, I don't buy it, but I am convinced because I'm looking at a perfect parallelogram. These sides are parallel, these sides are parallel, they're parallel, they have equal lengths. And of course, my intuition tells me that we would end up at the very same point. So I am convinced that traveling according to the vector a and then according to the vector b will put us at the exact same point as traveling according to the vector b first and then according to the vector a. So commutativity has been established. Let me put a check mark here. We are convinced. Now let's talk about associativity. So associativity involves three journeys, one according to the vector a, one according to the vector b, and a third one according to the vector c. And what does associativity say? It says that if you combine the first two journeys and summarize it with a single vector, capture it with a single vector, that's called a plus b, and then follow it up by the journey according to the vector c, you would end up at the same point as if you traveled according to the vector a first, and then traveled according to the sum, to the combined journey, according to the vectors b and c. So once again, this looks innocent enough, and this is the sort of thing that we're perfectly used to when it comes to numbers. But with geometric vectors, we're yet to understand what it means, what the interpretation is. So let me pick up a blue piece of chalk and draw in the interpretation of what we're seeing. Let's look at the left-hand side first. First, we're invited to combine the journeys a and b. And here's the journey a, b, and the journey c. So combining a and b is captured by this vector. So this right here is a plus b. Okay, and then a plus b followed by the journey according to the vector c from the point where we ended up puts us, according to our usual addition rule, right here. And it is captured by, does this deserve a different color? No, let it stay white. But it's captured by this vector right here. So this vector that I have already drawn in is a plus b plus c. So it reflects the left-hand side. Now let's interpret the right-hand side. Well, let's first find out what b plus c is, what it looks like as a single vector. So here is b and here is c. And for that journey, for the journeys according to b and c, this is our starting point. So b plus c, according to our rule for adding vectors, is this vector right here. All right, this is b plus c. And our picture is getting a little messy, but still perfectly manageable. And then the right-hand side tells us, combine the journey according to the vector a with the yellow journey that we just established. So this is our starting point, and we travel according to the vector a, followed up by the journey according to b plus c. And we end up at the very same point. So it doesn't matter how you combine journeys into a single journey. So as far as I'm concerned, associativity is verified beyond a shadow of a doubt. Even someone who loves mathematical rigor would have to accept this argument. So I'm completely convinced, and I just want to mention one important takeaway. Since it doesn't matter how you combine the terms, or how you combine the vectors, or how you combine the journeys, you can drop the parentheses altogether, because anyone can throw them in any fashion whatsoever, and associativity tells us that the result is the same regardless of how parentheses are placed. So we might as well drop the parentheses altogether because they don't matter. We will still sometimes use parentheses, but for intuition and interpretation and all of those other auxiliary purposes, but not for the purposes of changing the answer, because the answer doesn't matter. So we can drop the parentheses altogether and call this vector right here simply a plus b plus c. And it's very important to realize that it's associativity that allows us to write expressions like this. So associativity has been taken care of. So let's move on now to the most sophisticated of the three properties, distributivity. And I'm saying that it's the most sophisticated because it combines addition with multiplication by numbers. And here's what it's saying. If you take some number alpha, and we'll denote numbers by Greek letters, excuse me. If you have some number alpha, we'll use 1/2 in our example. It doesn't matter whether you multiply each of the two vectors by that number first and then add together the results, or whether you add the vectors first and then multiply the sum by that number. So here's a picture that's attempting to capture the distributive property. Let's start this time with the right-hand side. On the right-hand side, we're told to add the two vectors first and then multiply them by, we'll use 1/2. So here's the vector a, here's the vector b, here's the vector a plus b, according to our usual rule for adding vectors. So that's a plus b, and then we have to multiply it by 1/2. So halfway, there you go. We're right here. This right here is 1/2 of a plus b. Now let's draw the left-hand side, which is 1/2 of a plus 1/2 of b. And if we end up at the very same point as we just did, then distributivity holds. If we end up at a different point, then it doesn't hold. And then we would be in trouble because, of course, it holds. And here's how we see it. We will first take half of A, which is right here. This right here is 1/2 of A. And we'll add to it, now that we've arrived here, we'll travel according to not B, but half of B. So this right here is 1/2 B. So half of A followed by half of B. And are we arriving at the same point as having traveled full journeys, A followed by B, and then dividing it in two? And I'm convinced that yes, we arrive at the same point. Now, if you studied geometry and you liked it, then you'll remember this as a pretty advanced theorem that the line connecting the medians of two sides of a triangle is parallel to the base and half its length. So in geometry, it's actually a theorem, but we're not really concerned with proofs right now or rigor or anything like that. We just want to convince ourselves that these properties indeed hold. And I'm convinced that we arrive at the same point. It just makes total intuitive sense to me. So that's great. So distributivity has been confirmed. I forgot to put a check mark for associativity. And now distributivity deserves a check mark as well. So we have established 3 essential properties for the rules for adding geometric vectors and multiplying them by numbers. And these properties are actually typically required in order for certain objects to be considered vectors. Now, when I define vectors, I was a little bit, for lack of a better word, loose with my definition. I only mentioned a couple of things from the long list of required properties. The properties that I mentioned was just the ability to be added together in some mathematically clear way and being multiplied by numbers. But if you look up the definition of a linear space or a vector space on Wikipedia or Khan Academy, and for the love of God, please don't go to those sources to learn linear algebra, you will actually see these 3 and a few more properties as requirements for objects to be considered vectors. Well, I think that these are actually straightforward, and we can just think of them as properties that can be verified for the definition that we gave. And we have succeeded. So this was a pretty good video in which we confirmed these properties and interacted with geometric vectors in pure geometric terms.